couple of distinctions. Shortly thereafter, he was awarded the Young Investigator Award from the ATU for the cryosphere section, and that's a fairly major award for young scientists, and it's a good indication of his respect amongst the cryosphere community. And a couple of years ago, he was also awarded a Presidential Early Career Award for Engineering and Science. That's from the White House, and that's another good award for young investigator. So, without further ado, here's Ian.
All right, thanks a lot. Oh, I need the clicker. I can do it manually. That's it. Oh, here it is. I found it. You can remain calm. All right. Well, thanks for having me. It's a real honor to be here and with this group of speakers. So usually the beginning of my talk, I have to spend a lot of time kind of putting up the motivation for why we care about sea level rise, and I don't really have to do that here, I don't think. So in Ohio, the motivation is that when you retire, you won't have anywhere to go to because Florida will be underwater. But I guess from here, you're going to feel it directly. So we've already heard a little bit about ice sheets and abrupt climate change, so that's a nice segue into kind of the present picture. So you can ask, are the ice sheets collapsing? And if you ask most paleoclimatologists now, the answer to that is, yeah. I mean, we've got a very good record. We know what the temperature's been like in the past. We can look through to past times like the Eemian, which was the interglacial before the last glacial maximum. And we can see that the temperature was a little bit warmer than today, not a whole lot, maybe a degree at the most. And then we can look at what the ice sheets were like then. And sea level was a great deal higher than today. So sea level was still maybe 6 to 10 meters higher than now. So about the same temperature, but the ice sheets were much smaller. So that would tell you that we're going to lose some more ice. Okay? So when we talk about are the ice sheets collapsing, of course it's a loaded question. We've got to define what exactly collapses. So collapse could look like this, and this is probably what it looked like during the Eemian. So this is the Greenland ice sheet, one of our last remaining ice sheets. And it was really kind of two ice sheets, an ice cap and a little ice sheet during the last interglacial. So when temperatures were a little higher than they are now. So if that's kind of the stable configuration for 1 to 2 degrees of warming, we can expect eventually Greenland to look like that. Okay, much different than the present ice sheet. So we can definitely expect some additional sea level from Greenland. So then the question really becomes rates. And rates are thought of much differently now than they were when I started grad school. So I went to grad school to look at glaciers because I like mountain climbing and I like being in the mountains, and I thought it'd be fun. So when I started grad school, I was interested in glaciers because they responded quickly to climate, and a lot of the focus was on glaciers and mountain glaciers in Alaska that were rapidly retreating, and the glaciers in the Alps that were disappearing, Rocky Mountain National Park, places like that. And that was under the old paradigm of the harbingers of climate change are going to be these small glaciers, and they're going to react at time scales that we care about. So when we talk about sea level rise, the clear canaries in the coal mine, so to speak, were the little glaciers. And then about halfway through graduate school, or towards the end of graduate school, things started to happen in the big ice sheets that said, hey, look at us. And especially the Greenland ice sheet did things that completely redefined our picture of how ice sheets work. So we've got 2 remaining ice sheets left because I guess the bolide took out the Laurentide. So we've just got these 2. And we've got a Greenland ice sheet that's in rapid decline. So we're something on the order of 300-400 gigatons of ice per year. And remember, a gigaton is a cubic kilometer of ice. Okay, so for an example, the 3 largest glaciers in Greenland have lost an equivalent of ice enough to, if you were to melt it, you would fill one of the Great Lakes. So we've lost quite a bit of ice from the Greenland ice sheet. And that's this curve. Does this have a... Yeah, great. Okay, so that's about 400 gigatons per year. 360 gigatons is about 1 millimeter sea level rise. So we're getting over a millimeter sea level rise from Greenland alone per year. West Antarctica is also undergoing a decline, although it's a little bit harder to resolve. And you put them together, and instead of showing rates, you show cumulative change, and you get this plot, and we see this kind of nosedive happening. This black curve is the combined Antarctic and Greenland mass loss over this almost a 20-year period. Okay, so we're losing on the order, we've gained on the order of a little over 10 millimeters of sea level just from the ice sheets. So this is the new paradigm. This is rapid change of ice sheets on a time scale relevant to people. And okay, they're changing. An even bigger source of concern is the fact that we can't predict this change. Nobody really, well, there are a few people that made warning signs, but nobody really predicted the big changes, especially we've seen in Greenland. They kind of took us all by surprise. And they definitely took the climate modelers and the ice sheet modelers by surprise. And really, when this started, ice sheet models were a little bit better than kind of a cube of ice at the pole melting. They weren't really treated with too much in the way of complex dynamics, so it's not surprising we were so wrong. But Stefan Rahmstorf has been pointing this out for a while. He comes out with a paper every year documenting how our predicted sea level rise is falling far short of what we're actually observing. So that's suggesting that our models are not doing a good job. We're missing some physics. We're missing some boundary conditions. And then the other part of concern here is that the paleoclimate record, again, gives us a wonderful history of past collapse. So we know the ice sheets can collapse at alarming rates. So if we go to the last glacial cycle, so starting from the pits of the last ice age and coming out of it through the Holocene, we have this rapid period of sea level rise. And it was broken up into these particularly scary times in which the sea level here was rising over 3 centimeters per year. Remember, current sea level rise is about 3 millimeters per year. So we're talking about a 10-fold increase in sea level rise rates. The beginning of the Holocene, and then these kind of little steps here, and then another pulse of 1.5 centimeters per year as the Laurentide was in its death throes, so to speak. And then we have this nice stable period called the most of the Holocene, or the later Holocene. We've done pretty well in that period. We've come up as a civilization. Lots of our agricultural practices came in this time. You got to wonder if it's a coincidence that this leveling off happened when humans got their civilization act together. And you can see that seems to be this coincidence here when there was a leveling off at about 7,000 meters, or 7,000 years ago. Anybody here know what happened about 7,000 years ago? Very important event. It's right there. It's the first evidence of brewing. So when you're trying to convince your friends that sea level rise is a big deal, you can tell them that there's a 1-to-1 correlation between rapid sea level rise and lack of beer. Okay, so that would suggest that collapse might be bad. But really, how bad is collapse? Collapse, again, is a loaded word. It just means deflating of the ice sheets, and that happens. Is that a big deal? Well, you can have bad collapse and you can have not so bad collapse. And I kind of think of it as a best case scenario would be a linear change. We're pretty good at dealing with slow linear changes. As a society, we can build bigger seawalls, we can adapt to them, we can ride them out, we can engineer our way through it. Okay, so if you think of a kind of a scenario where we have our current amount of ice on the planet projected out into time, and we have this kind of linear decrease over whatever relevant time scale we're considering, you can think of it as a ski slope. Okay, and so we're in Florida. Okay, so skiing has boards on your feet. You go down a hill when there's snow on it. So if you have a linear slope like this, you can have a nice ride through it, and we would call that an easy run. Now, if we start talking about nonlinearities in ice sheet collapse, where you have stable periods and then deep dives into rapid sea level rise and changes through time, which is more consistent with what we see in the Holocene record, what's that like? Well, of course it's going to be worse. You have to adapt to faster total rates of sea level rise, but I would suggest that as long as those transitions into more rapid periods of sea level rise are slow enough, so for the mathematicians, the first derivative of the rates are gradual enough and low enough, you could get through it. Okay, you could deal with it, depending on what that time scale is. So you could ride the slope and be okay. It would just be a little bit more difficult. Now, what about this scenario, where you have what we call a sea level cliff, or in this case, an ice sheet cliff, where you have a steady trend like we're in now, or apparent steady trend, but then you hit an abrupt event where there's a destabilization and you lose a bunch of ice into the ocean, you raise sea level quickly, and there's little or no warning. What's that like? Well, you'd want to have your wits about you because you'd probably hit the bottom of the cliff with a bad thud. So really, what we're worried, I would suggest that what we're most worried about are these ice sheet or sea level cliffs. Okay, these unknown changes that are coming up to us that we don't have time to adapt for, that we can ask, could they happen? So we have these cliffs in the past during the loss of coming out of the last glacial, these bends in the sea level curve. These bends in the sea level curve, here and here, maybe some others in there. It's hard to resolve exactly how abrupt those were because, as was mentioned, the resolution is not perfect. But then the question then is, are we heading for another one of these cliffs? And can we see it in time to adapt to it? So we're pretty vulnerable to these cliffs right now. We like to live near the ocean. I don't have to explain that to you. This is just a hypsometric curve showing the population density relative to sea level, and we like to live close to the ocean because it's pretty, and other reasons too. Okay, so we're vulnerable. We still need to define how vulnerable we are and what kind of collapse we need to worry about. It's going to help our investigation a lot if we can actually define what kind of rate we're looking for to see if we can get it out of an ice sheet. So one way to do that is to actually look at the amount of people that would need to be displaced for a given rise at sea level, or at a certain rate of sea level rise. Okay, so the current rate is roughly 2 millimeters per year, 3 millimeters per year, and nobody's really moving. David's still living where he is, so we're kind of at a zero exodus rate. So we could say we're kind of in a stable situation. Now, if we start losing ice and rising sea level at a rate of about 0.5 centimeter per year, we're going to start displacing people. And we're going to start displacing people on the rate of 400,000 or 500,000 per year. Okay? That's the equivalent to the rate of European decline. Okay? So when you are flooded here, you could just move to Europe and replace all the Germans that aren't having babies. Now, once we get up to 1 centimeter per year, things start to get interesting. Now we're equivalent to the total U.S. immigration rate. Okay, the amount of people, the net immigration to the U.S. per year. So we would need to double that to take in all the people that we feel bad for causing climate change and getting rid of their homes. Now, once we get up to 2 centimeters per year, then things get really bad, and we have to move Los Angeles every year. Okay, so we can start to say that centimeter per year is probably a good place to put catastrophic at. If we went to a sudden 1 centimeter per year sea level rise, we would probably call that catastrophic. Our civilization would have a hard time coping with that. So now we can ask, are the remaining ice sheets capable of contributing to and I would add sudden 1 centimeter per year rate of sea level rise? Okay, so we can back up now and think about this purely as a heat budget question. You got a bunch of ice you need to melt to create a centimeter of sea level. How do you do it? Do you have enough heat to do it? So 1 centimeter of sea level rise takes the equivalent of about 40 terawatts of power. So 40 terawatts is about twice the amount of power that all humans use on Earth. Okay? So you double that, you get the amount of heat you need to melt sea level rise at a rate of 1 centimeter per year. Okay, so that if you distribute that rate of heat over the entire half space of the globe, that's the equivalent of about 0.2 watts per meter squared of radiative forcing. Okay, so that's the amount of extra radiation you need to get to the surface of the Earth to cause a centimeter of sea level rise. And you can compare that number to the current radiative imbalance, so the extra heat we're getting at the top of the atmosphere. That's about 0.6 watts per meter squared plus or minus 0.4. Big error there. So the amount of heat we need to get a centimeter per year sea level rise is within the error, well within the error of our current radiative imbalance. Okay, we can't measure that amount of heat accurately enough in terms of global energy balance. It's very small. And you look at the surface radiative imbalance, which is also 0.6, an extra 0.6, plus or minus 17 watts per meter squared. So more than an order of magnitude greater. Okay, so we can say that kind of the main thing to remember before you fall asleep is that the ice sheets, the heat required to change ice sheets in a big way that's relevant to us is small. It's a tiny amount of heat, and ice sheets are ephemeral in the climate system. It's amazing we have them at all. We should either be in a completely ice-free state like we were during the Cretaceous, or we should be in an ice age, or a global snowball Earth state. It's kind of strange to have as little ice as we do. And another way to think about that is the energy needed to get a centimeter of sea level rise is the equivalent of heating the upper 200 meters of the ocean by this much. 0.005 degrees C. You couldn't even measure that. Okay, so we've got the heat to do it. But you still have to get that heat to the surface of the ice and melt it. Right? So somehow if you take all that heat and get it onto the surface of the ice to melt that surface and take it away as runoff. Okay, so 1 centimeter per year, if we multiply that rate, we get 40 terawatts. So we need to apply this surface, this total melt to the surface to get, this total heat to the surface to get melt. Okay, so we've got about 15 million square kilometers of ice surface that we can work with. We got to take away Antarctica, because Antarctica is well below freezing all the time, most of it. So we're not melting Antarctica, and we won't anytime soon. And then we have to take away the half or so that's accumulation zone high up in the mountains. That's always below freezing as well. So what you're left with is about only 1 to 2 million square kilometers of actually melting surface that you can apply that heat to melt. And so that is the equivalent of 20 to 40 watts per meter squared. So you need an extra 20 to 40 watts per meter squared, apply that heat to the surface to get a centimeter of sea level rise. Does that sound like a lot or a little? Anybody? A lot? Okay, anybody know what the kind of the typical greenhouse radiative forcing is? I guess I just showed it, didn't I? Well, yeah, so I mean that's an order 10 times CO2 forcing. So even in our kind of worst nightmares, we probably won't be able to do that. Okay, well, how about the ocean? And since this is the College of Marine Science, this is an appropriate place to go. So let's take that 1 centimeter per year and compare it to kind of ocean typical extra heat. So 1 centimeter per year requires 1.2 zettajoules, so that's just that watts, 40 terawatts over a year per year of energy. And then you have 360 square kilometers of ocean. And if you apply your typical rate of forcing, say half a watt per meter squared over that, so that's 6 zettajoules. Okay, so we get plenty of energy into the ocean that we can use to melt ice. And this has been measured. If you look at the last IPCC report, there's this plot here. The upper ocean is warmed by about 150 zettajoules, so we only need about 1.2 per year to melt all that ice. So we've got plenty of energy in the ocean. So really, the ocean has already stored up enough heat from warming to give us over a meter of sea level rise. It's already there. It just needs to get to the ice. So we can ask, how can that heat get to the ice? So the way the typical ice sheet marine margin looks like, we have the ice sheet up here flowing down to the marine margin. This is the ocean. And at the ice-ocean boundary, we typically have some bit of floating ice. Okay, so this is glacial ice that's reached the flotation level, denoted by this white line here. And it's now floating. Okay, so we have melting occurring at this ice-ocean boundary. So this is where we need to get heat to melt ice directly to contribute to sea level rise. Okay, so right now about a little over 2,000 gigatons of ice per year are melted. So that's the current amount of melt equivalent of energy transferring from the ocean to the ice. So a centimeter per year would require about 1.5 times that. We would have to increase the amount of energy getting to the ice by 1.5, 150, or double it plus half. Okay, but But, we need to consider the fact that only about half of this melting actually occurs at the ice-ocean interface. The other half occurs, the other half occurs at icebergs that were basically taken away and taken somewhere else and melted. Okay, those icebergs aren't directly contributing to sea level rise. They're already floating. And they were taken somewhere else where the ocean could transfer its heat. So only about half of that is actually melting at the ice-ocean boundary, or melting in situ. Okay? So that means we need to double that increase. We would need a 300% increase in the rate of melting at the ice-ocean boundary. Okay, that's a lot. I would think you're the oceanographers, so you can tell me if that's a lot, but I think that's a lot. Okay, so that would suggest that we actually need to consider ice dynamics, which is good because that's what I do, and so that's why I have a job. Okay, so we can take home another point. Ice sheet collapse and catastrophic sea level rise, so that's that 1 centimeter per year of sea level rise or more, is going to come from increased heat transfer from the ocean and mechanical ice sheet response. Okay, so whacking the ice underneath the water line and having the ice respond to that. Okay, we've already got all the heat we need already stored up into the ocean to give us catastrophic sea level rise plus. Okay, so it's already there. So what we need to know now is the answer to our question of whether or not we can get a sudden centimeter per year rise in sea level lies in the mechanisms and feedbacks at that ice-ocean boundary. Okay, the feedbacks involved with giving heat to the ice and then having the ice respond to that loss of mass. Okay, so now we can operate under the assumption that we have unlimited heat available. Okay, we're not going to deplete the ocean of its heat. So how do we get that heat to the ice? Well, we've got our two ice sheets again, Antarctica and Greenland. And in some ways they're very different, in some ways they're the same. They're different in the fact their climates are quite different. Antarctica is kind of isolated in the circumpolar current that kind of creates its own special circumstances of ocean currents that I'm sure Dr. Meredith will go deeply into tomorrow, so I don't have to, which is good because I don't know a whole lot about it. And then Greenland is much more connected to the global climate system in a real way. It gets slammed into by the stream. So there's different operators involved, but they both have the same basic pattern of how heat gets to the ice. So they receive heat in three different ways. Okay, they receive heat via these high salinity shelf waters. So these are waters that form near the ice edge where you have sea ice formation. That sea ice basically sucks the fresh water out of the surface layer, and that salty, dense water dips underneath the ice and delivers heat underneath the ice shelf. You also have tidal mixing, so the tides are going up and down, and so the ice shelves are going up and down too, and that actually creates a mechanical circulation underneath the ice shelves that brings heat from the surface underneath them. And then third, you have the intrusion of warm, dense water associated with subsurface currents. So these are intermediate or deep waters. And it's only been recently appreciated how important these are to these ice sheets, especially in Greenland. Now we can say that the top two here are not going to be that effective for giving extra heat to the ice sheet. They're kind of limited. You're not going to be able to get a lot of extra heat from those mechanisms. The third one, on the other hand, we've begun to appreciate how important those are. And so somewhat recently, there's been a big effort in measuring deep currents within these ice shelf cavities and within these fjords. And we have a pretty good idea, or a much better map, of how warm water intrudes into these fjords. And the answer is these warm waters can get surprisingly deep into these complex fjords and up into these cavities, which is kind of a new thing. 10 years ago, especially in Greenland, nobody really expected warm, deep currents to be getting up into these fjords and doing a lot of damage to these glaciers. I mean, it's kind of intuitive now, but you go back in the literature and there's not so much on it, especially in Greenland. So this is a compilation from a recent science review paper. But we have the Amundsen Sea embayment on this part of the western Antarctic ice sheet here. It's kind of a hot spot for ice sheet change. And so there's been quite a bit of measurements going on there, and we find very warm waters at depth within this embayment, going right up into the Pine Island Glacier, which is right here. Okay, so this water is having no trouble getting to the ice sheet and actually going into the subglacial cavity, the sub-ice sheet cavity, ice shelf cavity to melt ice. And we have the equivalent thing going on in Greenland. So this is the bottom half of the Greenland ice sheet. This is the Sermelik Fjord here with Helheim Glacier dumping into it. And a group went in and took CTD casts up the fjord, and they find very deep waters exceeding 4 degrees Celsius at depth within the fjord. So this is plenty of heat to melt ice with. And if it's that hot, if that water is that hot, how much can they change? So the point here is warm, deep water, deep ocean water associated with deep currents, geotrophic flows, boundary currents, have been found all the way to the ice-ocean boundary. We can assume a direct connection for these warm cavities. But not all cavities are warm, and I'll talk about that in a minute. There's the fact that you have deep currents, warm deep currents going into some glaciers and not to others explains a lot of the variability we see. What really needs to be understood is how cavity geometry controls the intrusion of this warm water, and that's very poorly understood because we don't have a whole lot of data to go off of. What I'm showing you is pretty much the state of the art in terms of the data that we have for constraints. But what we can see is that in this case, this cartoon is of Pine Island Glacier. Here's the ice, the glacier itself with the ice shelf. This is the continental shelf. With red is the deep water from the circumpolar current coming into the ice shelf and interacting with the ice-ocean boundary and melting ice. And as that ice shelf is retreating, and the grounding line, which is the boundary between grounded ice and floating ice, as the grounding line retreats, the deep water comes in right behind it. Okay, so it's following the ice sheet as the ice sheet tries to escape it. No escape. And the ice sheet can even try and go over this rise, over a sill and into an overdeepening, and the warm water just follows it. It can run, but it can't hide. So in Greenland, we have another thing we need to consider, and that's the fact that we have all of this fresh water that's been melted from the surface of the ice sheet, entering the ice sheet and traveling subglacially, and then coming out at the grounding line and interacting with the ocean water there. Okay, so this is fresh water, so it's not very dense compared to ocean water, so it wants to get to the top, wants to go to the surface. So what we end up with is fresh water coming out of the glacier base. This is the ocean, here's the glacier, this is the calving front where we're calving off icebergs. So fresh water comes out of the base of the glacier, rises to the surface very quickly, okay, because its buoyancy contrast is so great that it jets to the surface. And I've actually been in a boat in front of a glacier, and it's almost like a geyser out of the ocean. I mean, the bubbling kind of geyser of fresh water coming out to the surface is almost the side of the boat. I mean, it's got a huge amount of power. It actually blows icebergs away. So we've got this rapid, buoyant rising. We have entrainment and mixing. And so we basically create this pump that brings warm, deep water in behind it. Because as this fresh water rises, it creates you can think of it as a vacuum that sucks in this warm water behind it. So we can actually invigorate convective circulation of warm water at the fronts of these fjords by adding fresh water. And there's been some modeling studies done, most recently by Adrian Jenkins at Bass, where he's used plume theory to actually derive an analytical look at an analytical model of this melting. What he finds that the rate of melt at this ice-ocean boundary increases with the meltwater flux by a diminishing power here. But the point is, if we add more meltwater coming out of the base of the glacier, it's likely that we're increasing the melt rate. So there's an interesting climate link there that wasn't necessarily intuitive. And this probably helps explain, as does large variations in cavity geometry and the boundary current circulation in that particular area, it helps explain why melt rates are so variable. So this is a kind of a seminal work here, the first real cataloging of melt rates versus temperature beneath ice shelves in Antarctica, and what we see is a nice linear increase in melt rate versus temperature. And this is for Antarctica, and you can see a huge degree of variability. And so we have cold ice shelves that aren't seeing those deep currents, and we have warm ice shelves that are. In Greenland, we have a similar phenomenon where my PhD student actually derived melt rates for all of these fjords where we have data for around the Greenland coast. And and we see a huge variation in melt rates over an order of magnitude. Some ice shelves are melting at centimeters per year, some are melting at meters per day. Huge range, and that it's not exactly clear why that is. So we can measure ice shelf thinning pretty well. So that's looking at the rate that the ice shelf is actually thinning in response to what has to be melting. And so we see that variability, and it corresponds nicely to modeled deep ocean temperatures. So that's this red coloring here is deep ocean temperatures. You can see they infringe right along the continental shelf up into the fjords, and that's where we have these red dots, which are rapidly thinning ice shelves. And then if we go to the bulk of East Antarctica, much less change in the ice shelves, much colder water. The warm boundary currents haven't been able to penetrate deep into those fjords yet, or into those ice shelf embayments. So once we start seeing rapid thinning in these big ice shelves like the Ross or the Ronnie Filchner, that would be a clear warning signal that something major is happening. Okay, so now that's the current picture, but we're interested in increases. How are we going to increase the amount of melting? Well, in this case, we increase the amount of heat getting to the ice shelf, sub-ice shelf cavity to the ice-ocean interface, so we need to increase the strength of these boundary currents getting up onto the continental shelf. How do we do that? Well, those currents are mostly related to large-scale wind patterns and sea ice formation, and you guys can tell me a lot more about it than I can. Than I know. So I'll hopefully in conversations with you after the talk, I'll be able to find out. But really the link here is complex. That's all I'm really trying to convey. Okay? The direct link between ocean heating and melting at the ice-ocean boundary is not a simple one of simply adding heat to the ocean and having that heat get to the ice sheet. There's complex coupled ocean climate processes that have to be considered. So because of that complexity, we don't yet know a time scale between forcing and response. We don't really know the link between these patterns of circulation and anthropogenic forcing, okay, which is kind of what we really want. And we don't know what the maximum limits are. We don't know how much heat we can get, how much of an increase in heat we can get. We don't have that upper boundary yet. And if I'm wrong, please correct me, but I'd love to be wrong. Okay, so that's melt, which I don't know a whole lot about. I know a lot more about ice shelf buttressing, because now we need to consider the mechanical response of the ice sheet to melt. Okay, so assume we can get all that heat to the ice sheet. We can melt a lot more ice, increase the rate at which we're losing ice at the ice-ocean boundary, and melt and thin ice shelves. How is the ice sheet going to respond to that? So ice shelves are important to the ice sheet. Even though they're floating, they provide resistance. And they provide resistance by transferring stress. Okay, so the way to think of it is you have your ice sheet, grounded ice sheet, and it's pushing the ice shelf out in front of it like a plank of wood floating in water. Now, if that plank of wood rubs up against the wall of the embayment or the fjord, or if it comes into contact with an island, so it regrounds on some sort of protrusion in the fjord, it's going to generate resistance. It's going to generate shearing and shear stress where those contacts are. And that stress is going to be transferred back up to the ice sheet that's pushing it. Okay? So ice shelves act as kind of a buffer zone in terms of stress between the ice sheet and the ocean. And what happens is the ice sheet gets used to that extra resistance. Over time, it feels that thick ice shelf and the resistance it provides, and so it gets thicker than it would be if that ice shelf wasn't there. It kind of overinflates relative to what conditions would be like, stress conditions would be like if you were to take away that buttressing. So if we suddenly remove this ice shelf, we've got extra stress in the ice sheet that has to be dissipated through thinning. And so the ice sheet responds to that loss in resistance by accelerating and basically drawing down itself to come to a new equilibrium. Okay, so by thinning ice shelves and removing them, we cause a stress imbalance that causes rapid thinning of the ice sheet. It can be rapid thinning of the ice sheet. And so we already have lots of data sets showing this. The first real clear picture of this came in 2002 when the Larsen B ice shelf collapsed. And this was a pretty stunning event that happened kind of at the beginning of when we had high frequency satellite images to witness it. It was kind of an on-cue thing. The MODIS imager went up, the Aqua imager went up, and this ice shelf decided to fall apart right when that satellite went up. So we got pictures of it. And this is from the Scambos et al. Paper documenting the change that occurred following the ice shelf collapse. So these are the lines of the ice front back in time. So the ice shelf used to be here, extending out to here in the late 90s, retreated here in early 2000, and then completely disintegrated in 2002. And this is the Antarctic Peninsula, and these are all the tributary glaciers flowing down into what used to be the Larsen ice shelf, feeding the ice shelf. So you can think of it as they were the tributaries on the river feeding the main trunk. And once the ice shelf disintegrated, immediately all of these glaciers sped up in response. Okay, so these plots are all of near the terminus of the glaciers, the speed near the terminus of the glaciers through time. So time is on the x-axis and speed is on the y-axis. And you can see all of these glaciers underwent, or just about all of them, underwent acceleration following the loss of the ice shelf. This happened in Greenland as well at Jakobshavn Isbrae, which is one of the more famous glaciers, the fastest glacier in the northern hemisphere. So Jakobshavn Isbrae used to look like this. This is the ice sheet here, and this is the glacier. This is the fjord with the ocean and icebergs that's calving into. The color scale indicates velocity. So the warmer the colors, the faster it's moving. And at the end of the 90s, the beginning of the 2000s, we had this multi-kilometer retreat of the ice shelf. So the floating part of the glacier thinned and fell apart in a pretty dramatic way. And immediately, you can see the deepening of the colors, the same color scale between these two. So speeds increased immediately by a factor of 2. This is a plot of velocity from on the ice sheet towards the front, following this white line. Okay, so the white line here is this point is 0. So you can see the rapid increase in speed, reaching velocities approaching 15 kilometers per year. Okay, so that's 40 meters per day of ice flow. This is also happening currently happening in West Antarctica at Pine Island Glacier in a kind of a less dramatic fashion, but still very important. So we have melting occurring at the grounding line and a large steady increase in ice flow rates on the shelf. Okay, so this is kind of the same plot, just flipped around. So this is up on the ice sheet, speed going to the ice front. This flat bit's the ice shelf, and speed has been progressively increasing with time. We can see this change in the surface expression of the ice sheets. This is a recent paper by the University of Texas group looking at 4 decades of Landsat imagery. And the column on the left is imagery from the early 1970s of Antarctic ice shelves, and you can see that there's not a whole lot to look at. They're nice and flat white, mostly, on the ice shelves. If we go back now and look at 2011, same places, you can see a lot more texture. These are all crevasses. These are all big cracks in the ice shelf. And this is where the ice shelves are speeding up to compensate for their thinning. So they were stable. They were generating a certain amount of stress by rubbing against the walls of their embayments or their fjords. And then as they thin, they generate less stress. So they have to speed up to compensate. And that speeding literally rips the ice apart. And we can see that very clearly in the surface expression from the satellite imagery. All of these big crevasses opening up due to the increased shearing of these ice shelves. And is this just a matter of time before these ice shelves rip themselves apart? Remains to be seen. So not only do ice shelves have a buttressing effect, but grounded ice does as well. So remember, grounded ice is ice that's actually in contact with the bottom. So its thickness exceeds the buoyancy force of water. So it's resting on the bottom, and it hasn't yet lifted off the bottom to form an ice shelf. So you have this portion of ice that's rested on the bed. And if that retreats suddenly, it generates some resistance, also transferred onto the glacier. And this was only recently appreciated. So for instance, we have Helheim Glacier. This is a cross-section of Helheim Glacier. This black line is the surface elevation in the year 2001. This dotted line is the bed topography. And you see there's a shoal and an over-deepening here. And over the subsequent few years, there was a retreat. The glacier thinned, and then it rapidly retreated down into the bottom of this over-deepening. And as it did this, there was a rapid increase in the speed. This is the speed from up on the glacier to the ice front. And you see the speed increase from 7 kilometers per year up over 11 kilometers per year over a very short time. As far as the resolution of our data goes, this is instantaneous. There's a major retreat of the glacier, and the glacier suddenly increases its speed. There is no delay. We haven't yet been able to put out a GPS or something like that out on one of these glaciers to actually measure it when it happens. All of our data is from remote sensing, but it's at least instantaneous in at the resolution of our data, and that's bolstered by the fact that we can model this effect. So this is the data. This is the model simulations reproducing the data. So we have the same effect where we begin our retreat. Each one of these lines represents the geometry of the glacier at a time step, and the time steps are even. So this bunching of lines means the glacier wasn't moving very fast. And then it fell down into this over-deepening, and it retreated very quickly to the other side. And at the same time, we see this large increase in speed. Now, once it gets to the other side of the over-deepening, it restabilizes because it regrounds itself, and I'll talk about that more in a minute. So we've gotten a very clear picture from remote sensing of these changes in glacier front length. Okay, so glacier retreat, grounded glacier retreat, and acceleration. So this is a picture, this is a radar-sat image of southeast Greenland, and color on it, the color layering on it is velocities, surface velocities from interferometric SAR. And so the deeper colors, again, mean faster. And then this is the same image with acceleration instead of velocity. So here, deeper colors means a larger change, a larger acceleration. And each one of these dots represents retreat. So the bigger the red dot, the bigger the retreat. And you see a very nice correlation between the more the glacier retreats, the faster it speeds up. Okay, so this is a very straightforward force balance effect. So we can say that loss of resistance from the ice shelf thinning, loss of ice shelves, or retreat of the grounding line, the perturbation in the stress, the resistive stress the glacier feels, kind of like taking the cork off a champagne bottle, that change in stress leads to an increase in discharge to the ocean. Okay, so there's this cause and effect between retreating the glacier or thinning the ice shelf and losing the ice shelf, accelerating the ice, and dumping more ice into the ocean. Okay, it's a very simple loop between change in glacier geometry and increased mass loss and sea level rise. So what we're interested in then is the rate, magnitude, and duration of this increased discharge. Is it going to happen quickly, just a little bit, or a lot? How long is this going to last? How much ice are we going to lose? And that's going to be dependent on the rate, magnitude, and duration of retreat then. Okay, that's the perturbation at the ice-ocean boundary caused by melt. So then we can simplify more and say what controls the rate, magnitude, and duration of retreat then. Focus on retreat. Okay, so we have some theories to rely on for the idea of unstable ice retreat. Okay, because it's this unstable, rapid retreat that would give us rapid discharge. That's what we need to get this catastrophic sea level rise. So the first is the kind of, in quotes, because it's widely cited and referenced as the marine ice sheet instability. And this was first proposed by Hans Wirtman back in the mid-70s. And this simply says that if you have an ice shelf or ice sheet with an ice shelf that's grounded on an inwardly sloping bed, so the bed gets closer to sea level as you get to the ice front, which is common of ice sheets because ice sheets are isostatically depressing their beds. So it's typical for the ice to get thicker as you move inland and the water depth to get deeper. If you have this ice shelf, this grounding line begin to retreat down this downwardly sloping bed, it can't be stable. And that's because as the grounding line retreats, it retreats into thicker water. And the rate of ice discharge across the grounding line increases nonlinearly with the thickness of the grounding line. So the thicker the grounding line is below the water level, the faster we lose ice. So you get this feedback between rapid discharge through the grounding line, increased discharge through the grounding line, drawdown of the ice behind it, because we're spewing more ice out, so we're thinning the ice, and then we have thinner ice relative to flotation level, so we we retreat more, increase the discharge, and you wind up with this feedback. Okay, so this theory was developed just for glaciers and cross-section. So it assumes no flow in or out of the screen, just flow along this x direction. Okay, so more recent work with more complex models has shown that you can actually stabilize a grounding line on a reverse slope if you include that flow in and out of the screen, or transverse flow, but I won't go into that. So there's some question as to whether grounding lines are actually unstable on downwardly sloping beds. And the fact that we have grounding lines that are on downwardly sloping beds in Antarctica, and they're not moving that fast right now. So it seems less likely that that instability would be an imminent threat. Okay, the second instability is the tidewater, what we call the tidewater instability. Tidewater glacier refers typically to a glacier that has little or no floating tongue. It's just the calving front and then the ocean in front of it. So you can think of the forces at the front of the glacier where the ice meets the ocean as the ice pressure, which is dependent on the thickness of the ice pressing down on the bed. And then that's feeling the upward force of buoyancy caused by water at the front. So there's always this force of buoyancy trying to lift the ice up the bed. And the greater this buoyancy, the greater the force of buoyancy, the less stress there is at the bed. And so the more the glacier slips. Okay, so you can think of a big ice sheet sitting comfortably on the bed, lots of stress generated at the bed. It's going to have lots of resistance to slip. It's going to generate lots of friction. But the more we melt ice, the thinner the ice gets, the lower ice pressure gets, the higher the buoyancy gets, the harder and harder a time we have generating friction of the beds, the more we slip, the more we speed up. Okay, so what this effect does is cause a hysteresis instability and instability threshold. So in this plot we have some unitless discharge, so the amount of ice coming across the grounding line that increases along x. And then on the y-axis, we have the thickness of the ice at the front above flotation as a percentage. So this 10 means 10%, the ice is 10% above flotation. Okay, you've got 10% more ice than you need to stay grounded. And we have two arms on these hysteresis. We have a stable arm and an unstable arm. So first is the stable arm. So in the stable arm, the discharge scales with thickness above flotation. So if the ice gets thicker, we increase the discharge, and if the ice gets thinner, we decrease the discharge. And this is stable because what it means is that if we thin at the front, so if we have our ice block here, and we have some ice coming in from the ice sheet and coming out the calving front, if we thin, we're going to slow down. We're going to drop down this arm of the hysteresis. And if we slow down at the calving front relative to the ice coming in, that means on net we're gaining ice. Okay, so there's still ice coming in to replenish, to keep the glacier stable. Okay, we've actually gone to a positive mass balance over that section of the glacier. The problem is, though, once we thin and thin and thin and get to this critical reversal, this instability threshold where we swing over to the unstable arm, now if we thin, we actually increase our discharge. Okay, so going back again to the balance of ice coming into the glacier and coming out the front, if we thin a little bit, we're going to increase the amount of ice coming out the front. Now we have more ice going in than coming out. A thin, and it's going to keep going down this unstable arm until it disappears. Okay, the only way it's going to restabilize is if it retreats back up to higher ground and gets more thickness relative to sea level. So this is a particularly effective way of getting rid of a lot of ice, as we've seen in Greenland and Alaska. And it has two major implications from this instability. The first is that there's a triggering event that switches from stable to unstable thinning. Okay, so if you have a glacier that's happy, it's well grounded, there needs to be something that draws it down to the thinning threshold, at which time it will go unstable. So you need a triggering event, whether that's melting or increased calving. We actually don't really know what that trigger is yet. That's a huge problem. And that can occur slowly over a long period of time, or it can occur quickly over a short period of time. Again, we don't really know what the case is. For example, for Greenland, we don't know if that was a long period of increased temperatures that thinned the glaciers, or if it was a short burst of warm water that did it. The other implication is that once the instability is reached, once you switch to the unstable arm, you're now independent of forcing. The reaction of the glacier is going to be only dependent on the mechanical feedback that you've launched yourself into. So it's going to be dependent on the bed topography and ice flow. Okay, once that trigger is pulled and you've gone into unstable retreat, you're now independent of external forcing. So the major implication there is if you're in unstable retreat and the climate's getting cooler, it doesn't matter. It's too late. And another one I'll throw in here is that this response, this implication 2, lags implication 1. The response lags the trigger. So you can have a warming event that happened 20 years ago that caused the ice to start thinning, and then nothing really happens, and then boom, you have a sudden, you get into the sudden unstable arm of the retreat. So that further complicates the picture. You can't assume a simple, it started retreating this year, so it must have been a forcing this year. So the critical variable then is bed topography. We need to know the bed topography, because if you have your typical bed like Helheim Glacier where you have a shoal, maybe it's a moraine, and then you have a deepening behind it, you'll have an area where the glacier is stable, an area where it's unstable as it retreats into deeper water, and then stabilization. So how far that retreat goes and how long that instability will last will depend on the extent to which you are retreating into deeper water. Okay, so if you were to expand this deepening into the interior of the ice sheet, you could have a scenario where you lost a substantial amount of ice very, very quickly. Okay, and again, we can reproduce this with models. This is the same figure as I showed before. Rapid retreat down into the pit. Then once it got to the other end of the pit, it stabilized, and the ice begins to slow as it thins and loses its driving stress. So then the critical thing here is, for each glacier, when is it going to go unstable? And is this instability going to occur regionally over huge areas? Or is it going to happen randomly at a bunch of different glaciers over a long period of time? Okay, so we're talking about synchronous or asynchronous instability. Are we going to destabilize the entire West Antarctic ice sheet at once? Or is this glacier going to go, and then this glacier? And the same for Greenland. We have over 200 big tidewater glaciers in Greenland. Are they all going to go at once? Or is it going to be really random and kind of, whack-a-mole style? So I would say that this is the critical thing in terms of figuring out if catastrophic sea level rise is going to happen. Is how synchronous these big instabilities are going to be. Okay, so we can go back to our ski slope here. And if we have lots of glaciers reacting at different times, that means that those responses are going to be spread out over a long period of time. So their cumulative effect in terms of adding to a rate of loss is lower. Okay, staggered sources from lots of different points. Okay, so we get closer to the easy slope. And I'd say that would be more tolerable. The more synchronous those instabilities get, if you start destabilizing large portions of Antarctica at once and dumping that ice into the ocean all at once, then your rate's going to go much higher. And you're going to get closer to a catastrophic level of sea level rise. So really, it's not enough to ask, are these ice sheets, is this instability going to come, or how are these ice sheets responding? It's really, what's the timing like? When are these instabilities going to happen at each one of these systems? Very complex thing to figure out. So for each of these mini glacier systems out there, we need to figure out some critical pieces of information. We need to figure out, will it go unstable? And to know that, we need to know its initial thickness and the rate of thinning that is bringing that thickness to flotation. Okay, how fast are we getting to that cliff? And then once it happens, external forcing no longer matters. We're into the dynamic, the unstable feedback. How far will it go? And that'll be determined by bed topography. So we need to know that. And then how long will it take to get there, and what will be the change in discharge resulting? And those are relying on the ice dynamics, the inland advection of thinning, which brings more ice down into the outlet, and the total perturbation in the ice flow that will give us that increase in discharge, okay, give us that flood of ice. So we need to be able to, or we can ask if we can predict these instabilities, even for one glacier. Can we do it for one glacier? So for any given glacier, you need to ask these questions. How well can we predict the ocean forcing? That's going to be probably our trigger. How much heat's going to get to the ice front 50 years from now? How well can we predict ice shelf and grounding line response to that forcing? If we have a given melt, what's the response of the ice going to be instantaneously? How well what are our boundary conditions and how well do we know them? How well do we know just the bed topography, the shape of the glacier? The ice rheology, its structure with regards to ice flow. So, ocean forcing, College of Marine Science, you can tell me, hopefully. Can anybody tell me? No? I'd say probably not very well. How well can we predict ice shelf and grounding line response to that forcing? So for ice shelves, we can do a pretty good job. If you tell a model, if you give a model a reasonable source of heat, reasonable circulation regime, we can predict ice shelf melting pretty well. Calving margins, on the other hand, so tidewater glaciers is another beast because we can't predict the rate of iceberg calving. Okay, that's a very complex process that we are in our rudimentary stages of understanding. So in terms of the big glaciers in Greenland, we have almost no predictive capability in terms of ice fronts. How well do we know bed topography? Well, how do we get bed topography? We get bed topography from these airborne radars. You have to fly over these glaciers because the surface looks like this. You'd never want to walk across that. You would never come back, I can guarantee it. So you'd fly over with an airborne radar. You can cover a lot of ground with an airplane too. And in good situation, good scenarios, the error in your bed from your radar is going to be plus or minus 10 meters. Where we care about ice the most, so these fast-moving glaciers that are deep, they're wet, they have very crevassed surfaces, they're in narrow fjords, the error is more like plus minus 50 meters, even greater. Okay, so that's our uncertainty in just knowing the thickness of the ice. So is that okay? So we asked this question of sorry for the bad reproduction here. We asked this question of a typical model that's used in studies all the time of looking at ice sheet response or glacier response. And all we did was take a kind of a standard configuration and tweak the bed topography within that 50 meter, even less, 30 meter plus minus uncertainty, and see what the responses were. So starting with the same glacier, model it in time, just tweak the bed within the uncertainty and see what happens. What we found is that for some runs, nothing really happens. This is the ice front change, so negative 10 means 10 kilometers of retreat. This is the grounding line change, so the ice-ocean boundary change, about the same as the grounding line. And this is the increase in discharge as a fraction. So 0.2 means a 20% increase in ice discharge, okay, which goes to sea level rise. Okay, so for some runs, nothing happens of real consequence. But for others, just by changing the bed topography within the margin of error, you wind up with 20, 30 kilometers of retreat, 50 kilometers of retreat in some cases. Okay, and that translates into a 50% increase in ice discharge, whereas before there was barely any. Okay, just by changing the uncertainty in the bed. Okay, what about ice rheology? So this is the uncertainty in the parameters relating the stress an a block of ice feels to how fast it deforms. Okay, so stress-strain relationship. Some of the other parameters that go into that. So this is just in the case of a flatbed. Did the same thing, just tweaked the rheologic parameters. And so just looking at the discharge here, some have a very small 5% increase in discharge following a perturbation. Some have a 15% increase. Okay, but this is just on a flat bed. Now, if we add a more realistic bed with an over-deepening, it gets to be just as bad as the ice topography scenario. So some glaciers have very little retreat, very little change. Some glaciers speed up by 50%. Okay? And also notice the huge difference in the timing. Okay? Years of difference in this is time. So following the perturbation. Some don't respond till a decade after the perturbation. Okay, so getting back to that point of you can't assume that just because the glacier changed this year, the forcing was this year. Okay. So what that means is that we don't know the bed topography well enough, and everyone knows that. It's a huge effort to try and get beds. And we also don't know the ice rheology very well. And also, we don't know how the ice rheology changes on the flow. Okay, so let's get back to our question. Are the ice sheets collapsing? Paleo records tell us they are. It's hard to imagine an ice sheet lasting under even the mildest cases of anthropogenic warming, at least for a long period of time. So the question is rates. How fast will it happen, and how we'll be able to predict these sea level cliffs before we fall over them? And I would say no, there's no way we can predict them yet. We don't even know how thick the ice is. So we've got a long way to go to be able to just to know whether or not we're about to head over one of these cliffs. So with that, I'll leave it and I'll take questions.
You've got two mechanisms at least for sea level rise. One is the warming of the sea itself, and the other is the glacial.
Right.
As that sea level rise, does that not also have the effect of floating the ice and speeding it up so it's a positive feedback?
Yes, but remember that's so the sea level rise won't be equal everywhere, right? And there's been a lot of work trying to figure that out. Going back to the last glacial, when one ice sheet was contributing to sea level rise, did the other ice sheet respond to that? And that's a question we don't really have. I think that's thought of in terms of, are the forcings caused by warming of the ocean going to overwhelm any kind of steric sea level effect? But we don't have that kind of resolution to tell. If you take your kind of standard ice sheet model and then change the sea level by what you would predict by, from an IPCC scenario for steric sea level rise, there's not a lot that happens, but I don't really trust those models anyway, so. I need help. I think you actually had your hand up first.
I know you say you're still trying to understand the thickness of the ice. Have you found any tools that are useful for verification of when it's actually sitting on the bottom? Multiple units come to mind, or I know the airborne doesn't really penetrate the ice, does it?
It has a hard time, and that's because radars have limitations, and they basically it's where you're most interested in the ice is kind of the worst case scenario for a radar. The ice is wet because it's under a lot of stress, so it's generating a lot of pore water. There's a wet bed. The surface is really cluttered, and they're in these narrow fjords. And so it's very hard to get radar waves to penetrate that. And there's been other attempts at other methods, but so far that's the only way we know to use electromagnetics to get through the ice. And a lot of work is going into improving those radars. And I don't mean to diminish their efforts. I mean, they're heroic efforts that they're going through to just get with the data we have. But it's a tremendously difficult task.
Can you comment on ice earthquakes and the potential for maybe not the buttress or the near field or close to the ocean ice, but actually ice inland?
How icequake propagates inland?
Exactly.
Oh,
and
yeah.
This thing can
Yeah.
destabilize at a catastrophic.
Oh, I see. Well, so the icequakes themselves are kind of a symptom of a mechanical event. And it's actually still debated about what these icequakes are caused by. And the thinking there has evolved a whole lot over the past 5 years. As far as we know, it's either due to a big calved block of ice that suddenly destabilizes and then rotates and slams into the ice wall behind it. So you can imagine you've got the glacier coming down and you've got a big iceberg that's forming, and as it capsizes, the bottom of it slams into the wall. The other effect is that as you're capsizing that iceberg, you're displacing a lot of water, and that just the sheer the movement of the water is generating the seismicity. And it's not actually the source of the ice quakes is not yet understood. There's theory, but it's not proven yet. There is an effect, though, and it's this loss of resistance. And there have been GPS measurements taken from Helheim Glacier that do show an instantaneous speed up due to a seismic energy generating calving event. So not collapse size, but a big iceberg breaking off actually generated enough loss in resistance to cause instantaneous speed up of the ice behind it. And that was kind of the nail in the coffin for that, or the the smoking gun for that mechanism.
So you don't necessarily need to melt it, you just need the ice cube effect.
You need to break it off. And we don't actually know how it breaks off. That's a very important thing. Yeah.
I wonder to what extent it might be possible to influence what you presented with if you change the rate of formation in alkalinic deep water. You change the salinity structure enough to stop the formation or slow it down substantially. It would seem to me that your heat flux changes, and if you change the heat flux, don't you change what's going on?
That seems reasonable. I mean, there should be a negative feedback there, but I don't know what the latest is on that. Yep.
Related, is there much evidence for the upwelling of upper intermediate waters into these fjords? Empirical evidence, that is. And also, if so, is there any observed change that you know of that may be occurring?
Well, so we have direct measurements of these deep waters impinging into the fjords from the few places where we have measurements. So, for instance, Bass has generated very good data for Pine Island Glacier, which is kind of the poster child for this, because you have a clear example of ice shelf thinning, which is leading to acceleration of the ice sheet behind it. And that ice shelf thinning seems to correlate with warm waters impinging all the way into the shelf cavity, not just straight into the ice shelf cavity, but also over a shoal and down into a cavity. So as you're retreating, that warm, deep water is just following it. And so there is direct evidence of that. Yep.
So at one point, I think there was a notion that this melting ice was lubricating the bottom of the ice sheet and was causing it to go faster. And I think Sarah Doss came out and said, no, that isn't true. Where are we at with that?
Yeah, so if I gave this talk a few years ago, that would have featured prominently. The Zwally effect. Yeah, we can still talk about it. We actually have, that's a great example of kind of the full circle of science, where there's this novel observation of acceleration on the Greenland ice sheet very high up, so near the equilibrium line, that corresponds with seasonal melting. So that would suggest that water's getting to the bed, lubricating the bed, and the ice speeds up. And this is at a time when everybody thought of the Greenland ice sheet as kind of like the Antarctic ice sheet, not much melt getting to the bed, very dry, frozen to the bed. So that was one of the first big breakthroughs, that the Greenland ice sheet's actually a lot more like a little alpine glacier than an ice sheet. So the kind of the natural thing to do there would be to attach the climate significance of that, or to extrapolate that to say, well, if we have more warming, more melt's going to get to the bed, more sliding is going to occur, and we're going to dump more ice to the ocean, and that's going to accelerate the whole process. But as we've been, there was a whole flurry of studies that went into that. And the piece you need to add there is the plumbing system, the transient plumbing system of the glacier. So what that means is, if you have an initial amount of water going into the bed of the ice, there will be some plumbing capacity at the base of the ice sheet to funnel that water away. And initially, that flood is going to overwhelm that system, and you're going to have an increase in pressure, kind of like a big jolt of water pressure in your plumbing system in your house. Okay, but unlike your house, the ice can melt. The pipes can expand through melting. So after a while, that increased throw-through of water, that increased discharge of water, works to expand the system, expand the plumbing system, and the plumbing system adjusts to compensate, and the water pressure actually decreases. And it's the water pressure that drives the increase in sliding. So you get a big increase in speed for a very short time until the basal system adjusts. And that's what Sarah's work showed, that was a very quick event. And if you have this happening at a whole bunch of point sources on the ice sheet, it kind of gets smoothed out into an overall small change in speed. And more importantly, there's a threshold in the speed where you trigger that reorganization of the plumbing system, that blowout of the plumbing system. But once that happens, more water doesn't matter. Okay, and we already reached that threshold anyways. Now, where it would matter is if you expand the area over which water is getting to the bed higher into the ice sheet. So then you'd be bringing heat and water to areas of currently frozen bed. And so you'd be initializing sliding in areas that don't currently have sliding. And on net, you would then increase the amount of ice migrating to the coasts. And we just actually recently observed that these lakes on the margin of the ice sheet are expanding upward onto the ice sheet with time. That in some regions, they've gone as much as 500-600 meters higher on the ice sheet over the past 10 years with increased melting. And that would suggest that potentially water could get to a larger area of the bed. And that's the focus of concern now.
So that image of lubrication is a flawed image. I mean, if we're trying to convey it in the simplest terms.
That's right. It ignores the transients. Yep. You've got to consider the fact that the ice plumbing system doesn't stay the same. And the funny thing is that the alpine glaciology community has known this for 30 years. And it's just they were two different communities. And I was actually at conferences in the past where the ice sheet people would get up and say, oh, the plumbing system of the glacier is going to speed up and blah, blah, blah. And then so-and-so would get up and say, well, Helmut Eichen in 1980 showed that if you put water into the bed, the plumbing system adjusts and you actually have a slowdown. And so it was kind of an example where two communities weren't talking to each other enough. And that's been fixed. There's a lot of crosstalk now between the ice sheet folks and the mountain glacier folks. So it's actually been a good thing overall. Yep.
Speaking of two communities, seismologists investigated calving frequency from year to year. I understand in the summertime that calving occurs maybe once a week, and now it's multiple times a week. I think Tim Dixon was telling me this earlier. Are seismologists able to detect this enough teleseismically to monitor it or
to an extent, but of course they can only see the biggest events. So there's actually a new project called GLISTEN that's headed by, I think, Lamont Doherty, Meredith Nettles, that just installed a whole array in Greenland over the past year or 2 years. And I haven't seen the results from that, but that's precisely the point, is to link teleseismic events to what you can actually see locally. And that should improve our picture of the mechanisms that we don't fully understand quite a bit.
We've had glacial events, at least 60, maybe more than 60 in the Pleistocene. And you would think that would have had an enormous effect on the bedrock. But the bedrock 1.6 million years ago beneath the glaciers must have been quite different than it is today. And number two, the question, reflecting what this gentleman had to say here, is there self-regenerative feedback during rapid, coming out of a glacial event? It takes 90,000 years to build a glacier. It takes 10,000 years to get rid of an ice sheet. That's certain. The rise in sea level, what really is the cause of such a rapid disintegration of the ice?
I can't answer that question. It definitely is something that needs to be considered. So most of the glaciological work that's occurring right now is simply focusing on the climate forcing, the ocean climate coupled forcing. And yeah, and the sea level part of that, the feedbacks of rising sea level and that effect on the ice sheet is an important part of it that we haven't even really gotten to yet. And it definitely needs to be explored. And hopefully the paleo community can give us more information about the importance of that.
What did that do to the ice sheets? It must have really created that.
We don't even really know where it's from yet, though, where the meltwater came from. So one big difference between the last glacial, coming out of the last glacial and now, is that you had these ice sheets that were that kind of covered part of a continent. So they were on the northern fringes of the continents of North America and Eurasia. And so as they retreated, they grew these giant lakes that we heard about. And that definitely helped get rid of the ice. And there's been actually a fair bit of modeling showing that once you build giant proglacial lakes, the feedback that kicks in between melting at the front, the loss in pressure at the front, the elevation feedback, where as you thin, you warm the ice at the surface, and then you thin more. All those kinds of conspire to cause rapid deglaciation. The piece that's missing from that is the effect of the marine processes that I've been talking about, because those marine margins they're not preserved. We can't really study them now very well, and the records are not very well known. But what we're seeing on it's kind of this back and forth where we get information from the paleo community that helps inform us, and then we get information from our current observations and our models that we can then go back to the paleo record and examine in a fresh light. And so some of the events that must have happened in Baffin Bay and the northern part of the Laurentide that was marine terminating are being reevaluated now in the context of what we're seeing. But the sea level effect is not well known.
Based on all the observations or the remodeling or
Yeah, so there's actually a lot of debate that goes into, the argument is we have this limited amount of resources, where do we focus? Because we have 200 glaciers in Greenland, we have how many miles of coastline of Antarctica, we have events that happened in the past that are happening now. Where do we focus that effort? And we have a tendency to go where, to go to the scene of the crime. You're focused on the event that's already happened. And part of that's because we don't, as I say, we don't have the ability to predict where it's going to happen next, which would be the ideal, to catch this instability in the act. So people are focusing on places like Pine Island Glacier because that's such an obvious candidate. We can see we also have a tendency to go to places that we can measure easily, either through logistics or because the changes are so big that we can see them from space. And, in all of our observations, we have a signal-to-noise ratio, and you can improve that in two ways. You can decrease your noise, or you can go somewhere where the signal's bigger. And we tend to do the former because it's much easier to do, and that's all we can do. So we have good data from a few places, a lot less field data, and there's a big debate right now. In fact, there's a big conference focused on Greenland in a couple of months. That's that very question. Where do we go with limited resources? So hopefully we'll be able to answer that.
You have one of these very large events. Is there any appreciable historical rebound that happens in the underlying? Does that influence the profile?
The bedrock profile? From what I've heard, it could. The problem is it's only been fairly recently that we'd have the ability to actually observe that. So for instance, the PoleNet program, which is mini GPS stations put around the Greenland ice sheet and the Antarctic ice sheets, those have only been operational for a few years at a high density. And so you need to be close to the source to actually observe this. And so we're ready now for it to happen, but we need it to it hasn't happened. One of these big destabilization events hasn't happened for a few years now. So it's kind of that Parkfield scenario of waiting for the big one. So yeah.
So you really emphasize the idea of synchronicity between all of these events. Although I could walk 2 doors down and speak to a Grace guru, is Grace capable of recognizing the synchronicity?
I would.
That's why I didn't go down the hall.
Again, so I'm going to take the cop-out answer and say it depends on how you define synchronicity and what the time scale is. And Grace has big problems with observing point sources. It can't really do that. And also the timing of the event. Because you can imagine you have an increase in discharge at a calving front. There's going to be when that discharge increases, there's an instantaneous increase in mass loss. But it's all concentrated across the calving front. That loss is going to propagate up into the interior of the ice sheet, and there's going to be some minimum resolution before which Grace can't see it. So Grace has to wait until that loss spreads out over the ice sheet enough to resolve it. And we don't actually know what that threshold is. We've actually been talking about that while I've been here. And it's going to take some modeling to figure that out. But it's a very important question. What can we see with Grace?
Could you delineate at least north or south?
In terms of a region?
Yeah.
If you give it a long enough time for that thinning to propagate, you can. But not the timing. I'm talking about time scales of years. It seems like, so the bigger the loss, the faster the time scale. So if you have one big glacier dumping a whole lot of ice, or a region of glaciers dumping a lot of ice at once, you're going to see that quickly because it's going to propagate into the interior over a large area quickly. If it's a lot of little glaciers here and there suddenly increasing, you're not going to see that for a long time because it's going to take a while for that. So basically, we can have the same amount of loss, same rate of loss. And if it's concentrated in a little place at the calving front, you can't see it. You got to wait till you take that cubic kilometer per year and you spread it over a large area, then you can see it. And it's actually the perfect opposite of what we can do with altimetry. So altimetry is really good at seeing point sources of loss. So if you have a rapid decrease in the surface, we can get that really well. We can't get the small thinning rates that are diffused over the interior.
So by difference?
Yeah. So the real power is going to come from combining the strengths of altimetry and Grace, and we're still just beginning to figure out how to do that.
You talked about synchronicity being the big issue here. So really, how much
Okay, so the way I would, so the way I understand that is, could you have one big glacier give us a centimeter per year? There's not, if you destabilize one of these huge ice shelves, and then what you're doing then is, so like the Ross ice shelf or the Ronnie Filter, if you destabilize that, then you're destabilizing all of the glaciers that feed it. And then it could be possible. There's no indication of that yet. So that, but even then, it's hard to get. It's really hard to get that much ice out of a glacier in a sustained way. So I don't have a precise answer for that, but it's important. Yeah.
We've had a breakup in the Wilkinson ice shelf, we've had a breakup in the Larson, and I guess, is there a consensus as to whether it's due to more water undercutting or is intercalating of melt ponds at the surface, and then they form cleavage planes and it lets go?
Yeah. So Larson and Wilkins are probably two different mechanisms, because Wilkins is a bit further south, so it doesn't have the surface melt that Larson B did. Yeah, Larson B was a clear case where you had surface melting doing a lot of work, because you can see right before the breakup all of these little melt ponds covering the ice shelf. And each one of those melt ponds is absorbing a huge amount of heat, transferring that to the ice, and it's also putting pressure on the ice. And once you have fracturing in these ice shelves and water filling those fractures, you have a process called hydrofracturing, where you have water that's more dense than ice filling a crevasse. So at the bottom of that fracture, you have a stress that's always going to be greater than the stress of the ice trying to fill it back in. So you have a mechanical feedback between cracking the ice and adding more water and going deeper and cracking the ice, and that just punches itself all the way through the ice shelf. It's the same process that brings water from the surface to the bed in Greenland. And once you cause a full thickness fracture in the ice of an ice shelf, that's it for the ice shelf, because it doesn't have any ability to hold itself back together. And then in the case of the Larson, you add to that the process by which you suddenly form all of these independent icebergs, because you fractured through the ice shelf. You basically chopped up the ice shelf, and now you have all of these icebergs kind of sitting next to each other that are unstable, and they all tend to rotate. So when that happens, they all push each other away. They kind of they act like a lever, and they push each other away, and that's probably what caused the explosion of the ice shelf. And I don't attempt to do movies anymore. I would have had the movie of the ice shelf blowing up, but it's a pretty fantastic thing. But that actually caused the shelf to physically explode out into the embayment. But so that was a clear case of surface melt having a big effect. There's probably some ocean effect as well that Michael Meredith will talk, I'm sure, a lot about tomorrow. But maybe don't feel like you have to. If you, Wilkins, we don't actually know what the trigger is there yet. It's an ice shelf that cracked and broke up, and we don't really know yet how related that is to instability. There hasn't been any response to it yet because the part that broke up wasn't well connected to anything, so it didn't generate any stress. So you lose the ice and there's no real effect. It's the same as Petermann Glacier, which I'm sure everyone heard about the past couple of years. The tip of that broke off. And it was a huge iceberg, but it was the part of the tongue that wasn't touching the walls or anything. So there was no resistance being generated. So there was absolutely no effect on the ice behind it.
I'm not very much about inputs, and maybe they're not all that important as far as snowfall is concerned. Is snowfall increasing in Greenland?
It is, yes, but it's not nearly enough.
The ability to make ice is rematched to
That's-
how much we're losing?
Yeah, well, it's the same as you mentioned, the slow buildup of ice in glacials and the rapid loss into an interglacial. It probably is related to that process. We only have one way to build an ice sheet, and that's snowfall. But we, as I showed, have lots of ways to get rid of an ice sheet. And so we don't see yet certainly the surface mass balance is important. And right now, over the past decade, the amount of extra ice we're losing from Greenland is about equal to the amount we've lost to increased melt. It's about 50-50. but you can't really do much. You can't get a huge pulse of melt over a long period of time to give you that big centimeter per year sea level rise. It's just, you need a dynamic effect, a mechanical effect to do that. And so it's still important in terms of ice sheet stability, but focusing in on the catastrophic level of sea level rise, it's not. I'll keep going until somebody stops me.
I guess I'll let.
All right. Well,
Completely lost track of time.
When
So.
when we picked this topic, I kind of had in mind the whole Arctic sea ice
Ah.
issue, which we're not really going to talk about. That's going to put you on the spot. But what year do you think we'll have?
All right. Well, thank you very much.
So I'm not quite worried. You know, this is going to be a huge geopolitical change when we have an not ice-free, but what we're
Yeah.
calling ice-free Arctic.
Once the ice leaves the glacier, it's out of my jurisdiction. Yeah, it's an important.
2018.
If I stock at some,
2018.
Okay, sounds good to me.
2018?
That's the word.
Why is that?
I'm betting a bottle of wine.
Oh.